So Helen Light's going to be our first speaker. She's going to speak about the Apalachicola River floodplain. Helen has been studying that floodplain, and that's in Florida, for those of you who don't know, since 1976, according to her bio. She has a long career as a wetland scientist with the U.S. Geological Survey, where she focused on the importance of river flow to the forested floodplains of the Apalachicola, the Suwannee, and other North Florida rivers. She retired from USGS in 2007, but continued to work through 2017 as a scientific advisor to the Florida Department of Environmental Protection, helping them in their efforts to protect the Apalachicola River and Bay.
Thank you, Melissa, and thanks to all of you for being here today. As Melissa said, I'll be talking about the tupelo cypress swamps of the Apalachicola River floodplain. They've been drying out and losing trees for decades. I'll explain how and why that happened and what it means to the ecosystem as a whole. Based on research that my colleagues and I did at U.S. Geological Survey and data that I compiled later as a contractor for the Florida Department of Environmental Protection. The Apalachicola River is the lowest 106 miles of the Apalachicola-Chattahoochee-Flint River Basin. The two rivers come together at the state line to form the Apalachicola River. This is the largest river in Florida and the largest forested floodplain in Florida. The floodplain's about a mile wide in the upper reach, widening to about 5 miles close to the coast. This is an intact river and floodplain system. There are no artificial levees separating the river from the floodplain. What that means is there's natural hydrologic connectivity between the two. And that, in turn, makes for a high diversity of habitats in the floodplain. That supports exceptionally high fish and mussel diversity, and this river floodplain system supports a highly productive Apalachicola Bay. This cross-section shows elevations, forest types, and water levels in the Apalachicola floodplain under more natural historic conditions. The highest elevations are typically close to the main channel on the natural riverbank levee. They support high bottom hardwoods, which are the driest forest type in the floodplain, dominated by sweet gum, water oak, and hackberry. Slightly downhill from there are the low bottom hardwoods with water hickory, overcup oak, green ash, and swamp laurel oak. The lowest and wettest forests are the tupelo cypress swamps. River water flows through the breaks in the levee via the floodplain sloughs to inundate the swamps. Under natural conditions in the past, swamp inundation occurred frequently in the summer, but not as much in the fall. The entire floodplain was usually flooded every year in the winter or early spring. So we're talking about the annual floodplain here. I'll be focusing mostly on the tupelo cypress swamps today. That's where the greatest changes have occurred because of lowered water levels. This cross-section represents floodplain in the upper 65 miles of the Apalachicola River, which is 10 to 25% swamps. The next 20 miles downstream, it's 45 to 50% swamps. And close to the coast, the lowest 20 miles is 90 to 99% swamps. So a cross-section in the lower 20 miles would be miles of flat, low swamp with just a very low natural levee where the bottom hardwoods were next to the main channel. The high bottom hardwoods on the upper left had the greatest amount of ground cover because there was a lot less inundation there, only about 3 to 4 weeks a year. The low bottom hardwoods had more sparse ground cover because they were inundated 2 to 3 months a year. And the tupelo cypress swamps used to be inundated 6 to 9 months a year. So you often saw standing water when you went in the swamps. Here are the data that allow me to tell you what happened to the tupelo swamps. We surveyed floodplain trees in the 1970s and again in the 2000s to see how the forest changed. The 2004 data set included subcanopy trees as well, which can give a good indication of the future canopy forest. The left axis is density, or number of trees per hectare. Swamps are usually a mix of species, mostly swamp species, but always a few bottomland hardwood species mixed in. That's what the colors are. The blue are the swamp species in swamps, and the red and yellow are the bottomland hardwood species in swamps in those 3 time periods. There's been a very large decline of 37% of all species in swamps from 1976 to 2004 in the canopy forest. And when you look at the younger subcanopy trees, it tells you that the total cumulative decline we can expect is 74% from 1976 to the future canopy forest several decades from now, when the present subcanopy becomes the future canopy. What has happened? Basically, it's become too dry for swamp species, but too wet for bottomland hardwood species to move in enough numbers to replace the lost swamp species. That sounds counterintuitive, but I'll explain it in the next few slides. Before I do, I want to point out that this graph shows the decline in the number of trees, not biomass, but with such a huge decline in density, a significant biomass decline is very likely underway now, 15 years later. In fact, some of the most sensitive swamp species were already showing a decline in biomass in 2004. Leaf litter productivity is a function of biomass, and a large decline in leaf litter productivity affects the entire river and bay ecosystem. This 1965 greenhouse study helps us understand what tupelo seedlings need and why they're not regenerating in swamps. Seedlings were grown under 4 moisture regimes. Saturated, moisture equivalent is what is the ideal soil conditions for most plants, 50% moisture equivalent, and the seedling on the right was watered, but only when it reached the wilting point. It's easy to see that those tupelo seedlings have to have saturated soils to grow tall. And that rapid height growth is key because the stunted tupelo seedlings, like on the right, they're not going to make it when the deep floods come the next spring. So what's happened is the summer flows are too low. The soils have dried out. It's stunted the tupelo. The bottomland hardwood seedlings could move in because they can do better in swamps with dry soils, but they don't grow tall as quickly as swamp species, no matter what the soil conditions are. So when the deep floods, which still come in the spring like they did in the past, come in, they'll kill the stunted tupelo seedlings and the short bottomland hardwood seedlings that moved in from the higher elevations. What we estimated as a result of this consequence was 4.3 million fewer trees in the floodplain. Those were primarily swamp species. With fewer trees, the canopy thins and more sunlight reaches the ground. This dries out the soils even more and allows ground cover plants to take over. On the left is what the swamps used to look like when I began studying them in the 70s. The photo on the right, taken in 2006, shows an exaggerated case, but everywhere we went, we noticed the ground cover was more dense than what you would normally see in swamps. Hydrographs showing how seasonal fluctuations have changed are better for explaining what happened to the tupelo than the average declines. Here's a typical dry year before flows decreased in 1941. The lower guideline shows the minimum flow of 5,000 CFS, and the higher line is the flow required to inundate the lowest 10% of tupelo swamps under current channel conditions, about 14,000 CFS. We'll focus only on the time of the year that the tupelo seedlings grow in height, so the fall and winter are grayed out. These were the periods with no inundation in the swamps that the tupelo seedlings had to endure in 1941 if they were going to survive. The 2 pulses in the late summer were great because heavy clay soils in swamps stay saturated for weeks after floods recede. But the period from April to July, which was about 2.5 months of no inundation, would likely have stunted tupelo seedlings to some degree, depending upon how much local rainfall there was in the swamps. However, when you compare it to a typical low-flow year in the later period, after flows decreased, you can see how recent conditions have been absolutely devastating to tupelo regeneration. after 5 months with no inundation, twice what we saw in the 1941 hydrograph, it's unlikely that any tupelo seedlings survived at all in 2011. I've put both of these years on the same graph so we can directly compare the two bars showing longest periods of no swamp inundation. In the next slide, these same blue and gold bars are stacked up for 33 pairs of ranked years, from the driest up to the wettest years. So you can see at a glance how this one example compares to all the other years before and after flows decreased. Here are the 33 pairs. They show the longest periods of no swamp inundation by using the blue bars in the years before flows decreased and the gold bars in the years after flow decreased. Drought years are at the bottom and flood years at the top. The example I just showed in the last slide, comparing 1941 and 2011, is the fifth lowest pair at the number 5 on the left axis. It's relatively typical of the low flow years, but even the years closer to average have huge differences between the earlier and later periods. It's no wonder that tupelo regeneration has plummeted because the natural flow regime has changed. Summer pulses that used to flood the swamps every year no longer exist in low years and are much less common even in average years. The floodplain is a matrix of habitats, not just forests, but also sloughs that serve as conduits for river water to get into the swamps through breaks in the levee. These very long periods of continuously low flows dry up the sloughs as well, causing fish kills when fish are stranded in shrinking, isolated pools with very low dissolved oxygen. In just this small area of the floodplain, there are over 20 miles of interconnected off-channel sloughs. These vast slough networks in the system are critically important to fisheries because they provide quiet, protected waters off the main channel where fishes can find plenty of food, shelter, and spawning grounds. Along the 106-mile river channel is a total of 409 additional miles of floodplain sloughs. Tupelo leaf litter dominates the detritus in the system. In a 1982 study, it made up 1/3 of all leaf litter in the floodplain. In both flooded forests as well as floodplain streams and sloughs, tupelo litter fall provides a major source of food and substrate for microorganisms and aquatic invertebrates, which in turn serve as the primary food source for floodplain fishes. The dramatic loss of tupelo trees and the likely decline in litter fall predicted as a consequence of that affects not only the swamps, but the sloughs, rivers, and receiving waters of the bay. Thank you for your time.